Okay, so we're going to talk about several concepts today. We're talking about residuals, residual plots, what the coefficient of determination is, as well as how to do standard deviation of a least squared regression line. So here we've got a little scatter plot. I'm just going to draw a basic little line of best fit. It may not be perfect, but something similar to this. So this is our y hat. So these are our predictions based off of our data. Um, what a residual is what is the difference? So a residual is going to be the difference between our observation, which is y, and our prediction, which is y hat. Very similar to what a deviation is off the mean, which is an observation minus the mean. So this is how we judge that. Now, what it looks like on the graph is this. This distance here. So any point that's above the line, obviously the actual value will be greater than the prediction, so we're going to get a positive number. Any number below, we'll get a negative number. And so these are our residuals. We can actually go through and plot these, and it tells us a lot about our data generally. So the way we set up a residual plot is this. Normally we'll have numbers on here, but this is just to show you what this is going to look like. So our first so obviously we've got our negative y's down here, got our positive y's up there, and these are our positive x's as we go along. So our first residual is positive, and it's just slightly positive, so we'll plot him there. Our second residual seems to be more negative, so we're going to move along the line and plot him down here. Our next one's a little bit less negative. Next one's positive. Next one's negative. So this is a residual plot. It may not look like anything to you, which is good. Generally, if there's really no pattern available on a residual plot, things are working out pretty well with a line being a predictor. Now, if we were to get some sort of pattern, that would generally say that a line is not the best way to do this. But we will stick with this example as we go. So this is a pretty good set of data to use a line for because we don't really have a pattern in our residuals. Now, the coefficient of determination, what this is it is going to judge how well, this coefficient of determination, which by the way is r squared, you've seen this before, it's going to judge how well our residuals are doing versus how well our mean would normally do. Okay, so just for a minute, let's look at these two different lines. So let's say we've got our line of best fit, which again, just guessing is like this. So residuals, again, are going to be the difference between these. Okay, so what about the mean of this whole data? So the mean of y. Now, I'm going to draw this as blue. So we're going to try to put this sideways, because the mean is just a flat number. We'll do the mean sideways. That's probably not about right, so it's probably closer to this, maybe. Maybe a little bit lower. Okay. So this is the mean. Okay, and so we'll call this y hat, because this is the average of all these functions. Well, if we were to look and say, okay, well, what is the how good is this at picking stuff out? So if we did residuals sort of based off of the of y hat, we have some very different values. So it's basically how well is this doing versus the other one. So while we looked up before and said that a residual is our y hat, or excuse me, our y minus our y hat, we do what's called the total squares, or the totals. That's going to be y minus the mean of y. Okay, and this is how we judge this. Basically, the coefficient of determination, this r squared, what it is this formula here, which is, and our calculator does a very good job of this, but it's good concept to understand. So this is going to be 1 minus the sum of our residuals, okay, squared, which is y minus y hat, divided by the sum of total squares, which is y minus y bar. So the theory here is this, that the smaller that our residuals are in comparison to the mean, the larger r squared will be. So in this case, if data is showing that it's supposed to be a line, and it's not a flat line, but a regular line, to show that we have a predictor that is much better than just using the mean here as our predictor, then that r squared tells us that there's really something going on with y when x changes. Not that y just kind of remains the same, or our predictor is not doing a good job. Thank goodness our calculator does this for us very naturally, but the idea is that we're judging our residuals, which is our predictions, how well our line is doing versus our predictions, versus how well our line is doing versus the mean, or how well our observations are doing versus the mean, because the mean is the easiest line to make. It is just an average, just flat line, versus a more complicated line, which it has a slope and a starting point. Lastly, when we talk about standard deviation of our least squared regression line, that's going to find the standard error off the line. So how much are we missing off this line? So I will draw this one more time. And we look at our residuals, because this again involves our residuals. The way that we look at standard deviation here, so the standard deviation of our least squared regression line, okay, this is a formula. It is the square root of the SS residuals, which we saw earlier, and we've talked about earlier, is the sum of our residuals squared. And this is the sum of squared residuals divided by n minus 2. So if you saw this in a different way, SL or L, this would look like this. The sum of, and excuse me, I forgot y hat. The sum of our y's minus our predictors squared divided by n minus 2, which is the number of observations minus 2. This is, again, difficult to find. It's a lot of typing stuff in, but there is a calculator shortcut that I show you on not only how to make residual plots, but also to find r squared very easily, r very easily, and also find your standard deviation if you need to. But you need to understand that it all starts with these residual values. How well is our line doing to predict our observations? How close are they? And we use r squared a lot to tell us that, but we also use our standard deviation, which is the formula here.